Welcome to Sensation and Perception, what I find to be one of the most fun areas of psychology to cover. A lot of this chapter goes in deep dives, and for our purposes, we'll be covering things much more lightly, and in particular as how they relate to things we've already covered. So, for our purposes, we're going to be going through this quickly with lots of examples, but with few examples that we are really going to have to know come exam time. Sensation and perception are clearly related problems and concepts, but they are also different in very important ways regarding how our brain interacts with the information our body is giving it. So, as mentioned before, we'll explain some important concepts, we'll focus on the example of vision and disregarding specific deep dives into other senses, and hopefully provide some fun examples as well. But first, quick true false. If people are told that an infant is David, then they are likely to describe that infant as bigger and stronger than if they are told the infant is Diana. Yes, that is absolutely true, showing that sometimes our schemas or our existing knowledge influence our judgments in a situation. Blind people, if you think that dreaming is a visual phenomenon, you may guess that blind people don't dream. They do, but may not describe it in terms of visual stimulus. This goes to show that since it is true, it seems to be that we have sort of a happy medium level of stimulation that we need. Too much or too little causes negative psychological and health outcomes. Advertisers can use subliminal messaging to limited effect. So it might have a small effect here or there, but it is not going to by itself determine whether somebody buys Coke or Pepsi or thinks of that company positively or negatively. This is one of those that it's so weird that it actually is true, which once again shows us the importance of vision in terms of dominating our sensory information and our judgments about the world around us. It's commonly believed that newborn babies are virtually blind and deaf. This is not true. They may be legally blind, but that doesn't mean they can't see or hear at all. For today's key concept, you may have heard of the McGurk effect, which is very cool. So for example, whether you're watching someone say something versus hearing them say something. So you're watching someone say ba, but the audio at the same time is them saying ga. What we hear is a completely, or what we think we hear is a completely different word. So once again, typically what we hear and what our eyes see are telling us the same information. When they diverge, we can get some interesting outcomes. What's also interesting is we can watch some gibberish mouth movements, and we can hear some gibberish auditory stimulus, but then we actually get some meaning from it, which just goes to show that we've been sensing, our senses are telling us gibberish, but what we perceive is meaning, showing the difference between sensation and perception. Sensory deprivation was previously viewed 100 years ago, for example, as a therapeutic technique for people with schizophrenia who are dealing with hallucinations. What we now know is that, first of all, that didn't help them, and also that sensory deprivation is viewed as a form of torture. So not only is physical torture generally frowned upon, but depriving people of sensation is also viewed as psychological torture because we need a certain baseline of stimulatory experience. Let's go through some common visual illusions. So of course, we think an elephant has 4 legs, and what represents the leg is different when we're looking from the top versus looking below, showing that oftentimes when we make judgments, we have to pay attention to only certain features, and we can't reconcile those with other features that don't fit the initial judgment. Here we see the impossible doghouse. It's tough to know which is in the front, which is in the back. And what we see is that, newborn babies let's say maybe 3-month-old babies will look at this longer than, for example, a regular doghouse, showing that even at that age, they have some basic understanding of what makes sense and what doesn't make sense. Here you see black dots seemingly keep appearing and disappearing. The only way to make it stop would be to fixate your gaze on one dot and stop moving. But of course, that's not natural. As humans, we want to shift our gaze all the time, regardless of what we're looking at. And as we'll see, our sensation perception process has adapted to help us better understand our environments when we're doing that, shifting our gaze. We also have the Mueller-Lyer illusion, judging distances based on certain cues such as angles. Is A and B longer or BC longer, or are they the same? You might say they're the same, but if you want, take the time and you'll clearly see if you measure it out that AB is substantially longer than BC, even though it really doesn't look like it. This is an example called the Ponzi illusion. The distance cues that we use lead us to believe that the monster in the back is bigger than the monster in the front, even though if you measure them out, they're the exact same size. We also see other examples of judgments. If you think these lines are sort of bowed out from the center, it is just an illusion. They are perfectly straight, but these other angle cues that give us sort of a distance effect lead us to believe that they have to be bowed. What do you see first, good or evil? I don't think that's predictive of much else important about telling us about our personality, but clearly you can see this one of two ways, and typically you don't see it as good and evil at the same time. It has to be one or the other. Finally, you may want to pause this to see if you can see something strange, something here that shouldn't be here, but I'll give you the answer right now if you're unpausing, and you can see the human head here. And once again, we're all looking at the same image, and since we already have a schema of what we're expecting to see, we're using, as we'll discuss later, top-down processing. I mean, we're really not paying it that much attention to what we're seeing because we already think we know exactly what we're looking at. This leads us into sensation, which is our sensory receptors in our skin, in our retinas, in our ears, for example, detecting something about our outside environment. So sensory neurons in our skin detecting touch or cool air or heat. Perception is the much more complicated process of our brain interpreting this information. So for example, you could be in a room for a long time and the air is slowly getting cooler, but perceptually, unlike the sensation where we're feeling this air getting cooler, our brain doesn't recognize it until all at once. And that's perception, when our brain becomes aware of this. We can also have sensory adaptation. Sensitization means we have increased sensitivity over time. So for example, if you eat a lot of salt, you are likely desensitized to salt. It's difficult to taste how much salt's in there because you're used to a lot. However, if you cut out salt, you will then become increasingly sensitized. So that means that you can taste differences in saltiness between foods, for example, different kinds of cheese that you couldn't taste before. These can take a while sometimes. They can take days or weeks or years. But in other cases, we'll show examples where you can become sensitized or desensitized in a matter of seconds. We also have this idea of an absolute threshold. This is more of a sensation issue. For example, dogs can hear, they're capable of hearing higher pitches than humans. For example, also children are capable of hearing higher pitches than adults. It's the absolute amount of a stimulus that our sensory system can detect. On the other hand, we have a difference threshold, and this relates more to our perception. So how much does something have to change before we notice a difference? I used to read outside a lot and watch the sunset. and many times I would get reading and it would be getting darker and darker, although I wouldn't notice it. Then I look up, and of course then I realize it's gotten quite dark, and that's when the difference threshold has kicked in. So think about if you're driving along and there's been a speed limit change. How long has that speed limit change been there? Well, chances are we're using top-down processing, and our environment that we've driven on that road looks the same as it has always, except for a key difference, and we're not very good at noticing differences in familiar environments. There's also the notion of subliminal. This is sort of the mid-range between sensation and perception. So for example, there can be a sound and you'll see some slight brain activity, which is evidence that yes, your brain has responded to that. But then you ask somebody, were you aware of that sound? And they'll say no. So there's a difference between when the brain is active versus when we are consciously aware of a stimulus. And some of that gray area is what we refer to as subliminal. And here we reach the big distinction that that sets up the basis of this chapter for us. Bottom-up processing is where we are using the information in our environment to make a decision. Think about being a child and going to a zoo for the first time, or going to an amusement park for the first time. And you see these giant rides that are moving fast and going high, and our bottom-up processing says, okay, this thing looks big and fast, and I don't want to do it. On the other hand, the adults might be saying, look, it's not a big deal. You'll go on it, and it's not that scary. And in fact, it's fun to be scary, because the adults have been on those rides, and they are using that past information to make the judgment. It's not a big deal. Just go and get on the ride. So for example, we want to use more and more top-down processing as we age. It allows us to see the world faster, and we feel more comfortable thinking we know all that we need to know. The problem is sometimes we get too fast in making top-down judgments, and we miss some important information in the environment that we didn't expect to be there, that we actually should pay attention to. Most of our decisions are some sort of combination between bottom-up and top-down processing, and we want to be aware of, are we using one more than the other, and does that balance represent what we should be doing? Quick review: detection represents the sensation, whereas interpreting or understanding or being aware of is the perception. Here's an example of contrast processing. This is called the Stroop effect. So you are trying to say the color and not the word. It's not very easy if you take the time to do it, because we want to top-down process the word first. If we see a word, it's tough for us to not try to read it first. And we're seeing this contrast. And also we have some left-right brain conflict, because of course the left brain wants to read, whereas the right brain might be more sensitive to the color aspect. Let's talk a little bit about vision and visual structures. First of all, we have the retina. It has what we call rods and cones. These are our receptors. Same thing for all of our other sensory systems, and we're just using vision as an example for how other systems work as well. We also have what's known as a blind spot. This is an area where the optic nerve leaves the eye, and there are no receptor cells there. So every time we open our eyes and look at something, we actually have a spot where we have no visual input. Why don't we see our blind spot? Well, because we have two eyes, and the part of the blind spot that one eye can't see, the other eye does have in its visual field, and our brain seamlessly integrates those two into one cohesive image. We want to distinguish between the cones and the rods. The cones are near the center of the retina. The lens is trying to focus the image onto the cones, because they are what allow us as humans to detect fine detail and colors. The problem is they need a lot of light. When it's dark, however, we can depend almost only on our rods, which are around the center of the retina. They help us detect black, gray, and white, especially in low light conditions and all forms of movement. So when we put them all together, we see that all these muscle and lens structures, the iris and the lens, they're all there just to focus light in the right way onto the fovea, which has our cones. And then on the periphery, top and bottom, we have our rods, which allow us, again, to detect black, white, and movement. Contrast the two. It may not seem like we have many cones, but relative to most other animals, we have tons of them because most animals are almost entirely driven by rods. And of course, for example, if you're maybe camping or in the woods at low light, you may see something out of the corner of your eye, and then you turn your head to look right at it and you can't see it because your cones aren't very useful, but your rods can still depict basic movement. Also, how is visual information processed? This is a little bit of a review for our neuroscience. We have our detector cells, our rods and cones, sends that information for the left and right visual field through what's called the optic chiasm, where it crosses over. And now we have our integrated left visual field and right visual field. Excuse me, this would be the left, this would be the right. And it also has to then go through the thalamus on both sides, and which then is directed to our occipital lobe in the cortex to process. So at various points in that pathway, we have neurons, and many of those neurons, even before the occipital lobe, have what are called feature detectors. They are neurons that only respond to very specific stimuli. So for example, there's been a lot of research done with cats to show that when you show a bar leaning slightly toward the right, that one feature detector neuron really goes crazy. Whereas other similar bars, but different orientations, register a very low baseline activity, which goes to show that there are very simple things in our environment that we have, in some cases, individual groups of neurons that respond only to those very basic things. We also know that sensory restriction is very problematic. So for example, if you take a kitten after birth and through the critical period for visual development where these feature detectors need to form and put it in a restricted environment with only vertical lines, once the critical period has passed, I don't know how long that is for a cat, but I would imagine a month or two would do it, take that cat out and it will never be able to perceive horizontal lines. It will be able to sense them, it will be able to see them just fine, but the brain won't be able to process them. And similar things can happen with humans as well, if we deprive them of their critical period for vision, for example. Here we have the classic Necker cube, and you can see either it facing the front facing the left or the front facing the upper right. And once again, it's showing that we can't perceive them both at the same time. We have to shift between one or the other. And this is, again, using our feature detectors to tell us what we're looking at and to perceive depth. We also have, for example, the top-down urge to see a shape, to integrate this into one shape, a triangle, versus what we're really looking at is three Pac-Man figures. We also have sort of feature detectors for movement. So of course, as you scan your eyes around the image, it looks like there is some movement of this. A more extreme example, so if you have epilepsy, you can feel free to skip to the next slide or advance the video. But you can see that the only way to make it stop is just to focus your gaze in one specific spot and stop moving your eyes. We also have color blindness. So as humans, some of our cones, males much more likely, can only perceive some colors. So do you see a 24 or do you see a 71? And that leads us into some interesting realities about how we perceive color. Stare at the center spot, keep staring, and you may need to pause. And eventually, what used to be gray surrounding that dot should go away. It should completely dissipate. And what that means is we're looking at the exact same thing. We're sensing the same image, but our perceiving has changed. And what this means is some of our cones and some of our rods are actively reacting to their situation. And what that means is sometimes they are sort of overstimulated with one color, which in this case is black or gray, and then they become hyperreceptive to white. So in essence, we are sort of hallucinating here, which is what a lot of optical illusions are essentially getting us to do. Here is the example of an after image. So you can stare at that center or at that figure on the left. Keep staring. You may want to pause this and give it a good 30 seconds, and then you can move to the right. And what you see is that where once you saw yellow, you should probably now see blue. Where you saw green, you should now see red. And what that means is we have what's called an opponent processing. So we have opposite colors. So as our, for example, our green cones get bored and overstimulated because we're looking at that same image for a good 10, 20 seconds, that means our red cones are getting hyperstimulated. They're actually ready to fire, even so much so that when we shift to a neutral background, there's no color. What they once were seeing green, now they're seeing red. So that shows that similar to color blindness, we have sort of yellow-blue and red-green links between color processing, which is basically to say, using our terminology, that our green color processors, cones, get desensitized, and our red cones get oversensitized, and then our yellow get undersensitized, and our blue get oversensitized, showing that the sensitization, desensitization process can take place in a matter of seconds. This is one of my favorite. Stare at that center plus sign, and what should happen is that eventually those pink dots should go away, and you should see a green circle around them. Now what's important to note is that is not a green circle. That is just removing each one of those red dots. And so you can see we have our basic red-green processing opponent process link. So when we're staring at that same spot, our red cones get desensitized and our green cones get oversensitized, so they're actually helping us perceive green when there is no green on this image at all. What this leads us to believe is that what we perceive is much more than a simple adding up of what we're looking at. And this is the fundamental idea behind Gestalt psychology. So, 100 years ago, a bunch of researchers got together and realized that there's so much more that our brain gets out of our environment than just what's physically out there. And so the Gestalt psychology suggests that the whole we get, our perceptive whole, is greater than just the sum of the parts. So here's some examples of being able to see different kinds of images. On the right, for example, do you see a rabbit or do you see a duck? We also have distance cues. So for example, this is the Ames room. Here's one orientation. Here are the same people. What's happening here? Well, if you view it only from that one specific spot, it looks like a normal room. Anywhere else, though, the depth cues have been strategically manipulated to create this illusion of depth. And this is not for exam purposes, but just to show that there's been a lot of not just science and academic research into extrasensory perception, but also military research as well. and there has been no replicable finding of ESP or any forms of parapsychology being able to perceive things on the other side of the world or predict the future, for example. Once in a while, you'll get a study that shows slightly greater than chance telepathy, but each time an attempt to replicate that has been made, that has failed. As we review, Gestalt psychologists emphasize that you might be tempted to say C, that is incorrect. The whole is more than the sum of the parts. We organize our sensations into meaningful patterns, much more than just simply adding up the sum of what we're looking at. Quick true false to review. Top-down processing does rely more on what we already know, and that guides our judgments. Sensation and perception are related, but they are certainly not identical. So this is false. Rods, by definition, are better than cones at detecting movement. Some things can be desensitized over years, but as we've already seen, some things can be desensitized in a matter of seconds. This would be false. We are actually looking for the absolute threshold here, the lowest amount that our sensory system can physically detect. Here's a common myth that reading in dim light can ruin our eyesight. There's no strong evidence supporting that this is true. And our key study today, this would be a sort of computer simulation study looking at our basic sensation perception. Can we perceive that there's happy and angry faces in the crowd? And are we better at detecting one, either angry or threatening faces when they're out there? So what you see is these kinds of examples flashed for just a split second. So fast, we'll talk about maybe 0.05 of a second. So 50 milliseconds. Very short time to really remember what we've actually seen. We could just say, I saw 9 heads. But do you think you saw an angry face or not in that image? And of this computer simulation, you would have maybe 100 or 200 individual trials. And you can't see the labels here, but how many faces, for example, are in the total matrix? And here would be happy faces. And as the matrix gets larger, there are more total faces in the crowd. We become less accurate at determining whether there was a happy face in there. The solid line represents the angry faces. And what we see is that it seems like there's a baseline of accuracy that seems to be pretty high, even in big matrices, that we can fairly accurately detect if there was an angry face in that crowd, maybe showing us that there's evidence of more adaptive feature detectors for detecting angry or threatening faces compared to all other faces. But that's enough for now. Hopefully you found a lot of interesting and fun things in this slideshow. I'd like to discuss these and more in the discussions. How did we develop this way? How are sensation and perception different? What are some examples that we've seen in our life? And how can we use this difference to help us in our lives as we navigate and perceive the environments around us? Looking forward to discussing all this and more in the discussions.